hello guys. Welcome to another episode of Xah Talk Show. We are going to code Wolfram language geometry. Okay, let's begin quickly. Let's just start. Yeah. So if you are here, say hi. Love to see your comments. If you are watching this offline, play at 1.5 speed and skip around because I ramble. Hello, Choker Man. Okay. So Wolfram language coding. So any questions, ask me about Wolfram language. Yeah, if you are watching offline, skip it around. Okay, so video check, audio check, good to go. So let's go. Okay, so let's stop this. Stop. Okay, so I have done like 100 videos on Wolfram language, so just search for it, you'll find it. So I won't be doing introduction today. So last time, about 2 weeks ago, we did this Wolfram language graphics for beginner, draw pedal curve. So that involves learning how to do graphics in Wolfram language and also mathematics of vectors. Okay, so watch that one. Today we're gonna clean up the code here. I'm just gonna show you some Wolfram coding. Okay, so let's copy that. We need to do some cleanup code here. Okay, so let's start a code block. So here is Wolfram language, and we need to. So let's go to the previous talk show here, and I want to copy some links. Okay. So we got this parabola curve and Wolfram language tutorial. Copy it. Okay, close. Okay, let's paste it here and remove the section. Remove that. Remove to do. Okay, showing browser. So that's today. So we got start to code. Okay, so so Wolfram language. Hello guys, say hi and ask me questions about Wolfram language. Okay, we're gonna focus exclusively on Wolfram language. Ergo, Massive, and Damsic. Okay, so Wolfram language. So let me just show you the code first. What does it do? So kind of flashy. So a new notebook. Let's magnify 125. Paste it and magnify. Okay, so we pasted the code. So we are defining this function. Here is the inline documentation. That's how you do it. The inline documentation. So shift enter to evaluate it. Then this part is the code. Now this part, shift control N to make it typeset so it looks better. Okay, then split, shift control D to split into two cells. Now shift enter to evaluate that. So now Wolfram language knows this function. Okay, and this is how we actually use the functions. Use the function shift enter. There it is. Okay. So we did the animation of moving the point, then you see the line change. Very fantastic. My job today is to update this code. Okay, so this code to kind of modernize it, because this code is like 2 years. This code is like 30 years old. Okay, so let me show you one by one. So first of all, so you got this code. So you got, I want to modernize the code, but also make it easier to understand, because right now in this code, I use a lot of the Wolfram syntax shortcuts. For example, this /@ most people wouldn't know what it means, or this ampersand. So remove that, turn them into more normalized standard syntax so everyone can understand it. Okay, so let's just begin. Okay, so this part, you see this part, the ampersand, that means a function. So that means whatever before it, this is a function. So this can be written like this. Okay, so what? yeah, so can be written like this. Let me just show you. Okay, so remove that ampersand and then x. Okay, so x x. Okay, so that is equivalent to that, but this can be further simplified. This @ sign is a shortcut. It's a prefix notation, so it is equivalent to x. Okay, that. Okay, so same thing. Let's do that. So these three lines are completely equivalent, okay? Because what Wolfram language does, that whenever you run a code, the first thing it will do is it will transform the syntax to the full form. So actually, this is equivalent to, let me do it again. So the pound sign just stands for the argument. You see, over here, this function is like a lambda. So x is a local variable, the bound variable, the parameter. So then you apply xf function to x and yf function to x, make them a list. But here is exactly the same thing, but just shorter syntax. So all these four lines are equivalent. Now, if you want to know about details, go to Wolfram language tutorial, search on xahli.info. Okay, and you go to the functions, go down, there's a section on defining a function. Then you go down, there is a function syntax shortcut. So that will explain, you see, examples of the equivalence between these various forms. So in this form, it's the shortest, cryptic, but nobody understands. But this, and then the second cryptic is this, because nobody understands what's the pound sign. So then this make it a bit more simpler. So you can see x is a bound variable, and fx at x and yf at x. This one is more everyone can understand. So let's use this one. Okay, so that's a sample. Okay, so let's just use that. So here n, what n means, n at. Okay, so here n at something, let's say 2/3. Okay, that is a shortcut notation for, like we explained before. Okay, so these two are exactly the same. So what does the n function do is that it changes all symbolic or exact expressions into numerical. Okay, so for example, you can just run it. Let's run it. Actually, I can run it here. Okay, so I can run it. Running for the first time takes a while. Wait, okay, so finally, you see 0.66, and this same thing, okay, the same result. Run it, same result, okay, but if you do this in Wolfram language, it's the same thing. Shift enter, see, and here, shift enter. Now, if you just do 2.3, it returns that exact result. For example, you can say 4 divided by 10. It will reduce the fraction, but you get a fraction, okay? So whenever you want numerical result, just slap a n in front of it. Okay, that's what this n do, okay? So now here I want, I want to say numerical, but let's remove it. I don't want numerical. So now another syntax, you see this range. Let me explain that one, okay? So usually, so usually you map a function to a list. Okay, so range is range means let me show you. Okay, 1 to 5. So that means apply the function f to range, just generate a list of numbers 1, 2, 3, 4, 5. So you get that. Okay. Okay, so but there's a syntax shortcut. So instead of writing that, you can write f map, not that. Do I have a shortcut? Maybe not. Okay, so you can. This is a syntactical shortcut. They mean exactly the same thing. So Wolfram language, whenever you run it, it will change all this shortcut syntax to the full form like that. Then it will evaluate. So they are 100% syntactically equivalent. So in some language, in computer science, sometimes they call it sugar syntax. But the sugar syntax in scheme Lisp, in JavaScript, they are not exactly the same. They are not exactly identical, okay? So, but in the Wolfram language, they are 100% identical, because whenever you run something in Wolfram language, it will turn all these syntactical shortcuts to this full form syntax. Like this is kind of like this fully nested. Then evaluate. So they are like 100% the same. So that's that's kind of one important aspect of Wolfram language syntax. Okay, now you can learn about this, what I just talked about, at this article on that. Let's see, global variables, local variables, conditional loop, iteration functions, pattern matching, data structure, and advanced symbols, principles, full form. Okay, so this article, Wolfram language full form syntax, will explain the details about what I was just talking about. And if you go to the full form versus syntax operators cheat sheet, this page will give you a complete list of all these kind of syntactical shortcuts. Very interesting, because this syntax system allows you to have infix notation. 3 plus 4 will actually become plus 3, 4. 3 divided by 4, or at least, so it allows infix notation. So this page lists all of them. Like you can learn all about them. So for example, the @ sign we mentioned before is right here. @ sign is just a prefix notation for f bracket x. Okay, so let's go back to clean up the code. So we are doing here, so this part, let's change it. So let's change it to the full form, because that's simpler to read. And map at, so this range, map at this range. Okay, so this line is equivalent to that. Okay, so let's just remove that. So now, okay, so next other things I want to change. Now remove. Let's see other things I can change. So hue, now hue is a color function. So it just represent red. Okay, so if you look up the documentation, hue is hue saturation brightness model for color. Okay, so you can read more about it, hue. But this 30 years ago. So today you have if you want red, close that. Let's go back here. If you want red, you can say red, just say red. Okay, so this is added, I don't know, maybe 10 years ago, more than 10 years ago, 15 years ago. So you can have blue instead of the hue something number. So in other words, you got named colors. Okay, so let's change this hue just to red. Okay, and hue 0.7 is blue because I memorized it by now. Because coding Wolfram language, hue 0.7 is blue. So I memorized. Now this part, this numerical result, let's remove it. So in Wolfram language, whenever you have an argument that's already approximate number, then the full expression will be approximate number. Okay, so you don't necessarily need the n. If your a and b or whatever the argument is numerical. So if you start with a exact expression like fractions or symbolic expression pi, then the result will always be symbolic and exact. But if you begin with a CPU number, like so-called by the C guys float or float, then the result is float. Okay, so why do I have an n there? Well, because when you are creating graphics, you don't need symbolic result. You don't want the all the computation of the graphics by using symbolic result, because it doesn't make sense, because you just want to see a graphics. So when you use approximate machine numbers, they become faster. That's why I put all these n to force them into the machine numbers. But it's not, but if you don't do it, then it'll still work, but it depends on two things. Depends on when you call this function, if your argument, for example, this min, max, if you are giving them machine numbers. If you do, all is good. But if you don't, then the computation will be done in exact numbers, so it's much slower. Fractions, they will reduce fractions and so on. But when it finally tries to show the graphics, it will still work. It's just slower. Okay, so the advantage of adding, forcing numerical result is that it's faster. It's always faster. But the disadvantage is that so the advantage of not having that n to force machine number is that you can control what kind of result you want. Because if you want numerical result, you just call this function with numerical inputs like this. But if you want exact fractions, symbolic computation, then you just use, for example, this 0.25, then you just say 1/4 instead, then you compute symbolically. But what is the purpose when you do graphics symbolically? Because sometimes you don't want just the graphics. Sometimes you want, this mathematical formula to create something. You actually want the result to continue to work with it. So that is why sometimes it's useful. Just sometimes, usually not. Usually when you call a graphics function, all you want is just a graphics. So anyway, so that's why I'm removing the n. Do that make sense? Okay. Do you do job or no? What kind of question is that? I don't answer that question. Okay. What like you want to pay me for something? So next, let's see. I want to optimize. So this part. So let's just again. Let me do that. So this one, let me rewrite this. Okay. So rewrite this curve points. Okay, and map this function. Okay, so this. Okay, so you don't need that. So that's, these two are equivalent. By the way, function has many other representations, many other syntax. Shall I go it? Hold on a second. So these two are exactly the same. Let me show you another representation for a function. So another representation for a function is that here, okay, so you just say x that, okay, x2 x, okay. So you can see this is also kind of familiar to a lot of people. So you got x is a parameter, this means a function, then this means return that, okay? So x is here. So these 3 lines are all equivalent, okay? Now, typically in Wolfram language, or Mathematica, if you code a lot, usually a lot of people just use that because it's easier to type, kind of. Anyway, so I don't want that. I want this function fully spelled out, okay? So these 2 lines are exactly the same. Wait, not the same, okay? So next, okay, so let's rewrite this one. Yeah, okay, so line, line is a function, fn, so we just want that. Yeah, so, and map this function to this. Okay, so these 2 are exactly the same. Wait, I forgot the line. Hold on a second. I forgot the line. You cannot forget the line. Wait. Yeah, so that. Cut. Now, in fact, we can actually just test it, okay? Just test it. Did we make some error? Run it. Oh, you need to clear it first. So clear it, then now code, then try this again. Fantastic. So far, still good. Still good. Now next one, we're gonna rewrite this block. Okay, paste. Again, it's a map. So you see, map is used so often. Okay, so map function to the curve points. And what is the function? The function is going to be, okay, this one. Cut, paste. Okay, so that. Okay, let's see. Map a function. This function is a line, and this line is a list of things, and the list got 2 things. One is this reverse normalized, and we got the n again. Let's remove the n for numerical result. Fantastic. Hello, I don't know. Okay, so this n for numerical result, let's remove it. Okay. Okay, so we got normalize. Normalize means turn a vector into a unit vector. Okay, then you reverse. Okay. Okay, this is vector geometry. You move, you do basically this part, you rotate the line 90 degrees. Yeah, that's what it does by this trick. Okay, then you increase the length by 100. Okay, so this part, okay, so let's just do that. Okay, so let's make sure it's correct. One double check last time. Okay, yeah, you sure? Yeah. Okay, then the last part, the show graphics, we don't actually now 30 years ago you always need to call show, but sometimes, like in 2005, you don't need to call show anymore. or you can just call graphics. Whenever you have a graphics, it will automatically show. So you remove the show and put the options here. Okay, so something like that. Okay, so something like that. Now copy that. Now go to the top, cut that, and let's copy the documentation. Okay, let's clean up the documentation. Let's remove the line here. Draws the negative pedal lines of a parametric curve xf, yf at points. Let's clarify this. Use English from min to max with step. Okay, so let's, instead of using code, use English to explain. Okay, so that is that. X and y must be pure functions. Okay. This part is a bit technical, and here's the example. Again, example using this cryptic notation, so let's not do that. Let's use let's convert it to a way most people would understand. Function file name. Okay, wait. Function, yeah, okay. So Wolfram, there's a abbreviation issue in my Emacs, but anyway. So let's make it verbose so that people can understand the most when you have verbose syntax. Okay, so that. Okay, so here's the example. This pedal plot function takes two arguments. The first one is a list of two functions for x and y. The second one is a range from 0 to 2 pi in steps of 2 pi divided by 30. Now you see, let's make it numerical. So when you put a dot after a number, that makes the computation using machine numbers, which is C++, what they call float. Okay, so here, and what is the last argument? So wait, min max step, and what is this x0? Oh, that is a pedal point. Okay, so we can kind of do that. So this is one thing. Okay, so instead of that, so these two are equivalent. So, but let's use the easy to understand one. Okay, so let's shorten the usage. Okay, so now copy that, go back to our new code here. So now copy all that, copy back to Wolfram language. Let's paste, okay, new code, evaluate it, it's done. Now let's call it here fantastic. And let's try an example we have here, negative pedal plot. So whenever you want to ask the inline documentation in Wolfram language, you just type the question mark and the whatever function name. So you see, it returns the documentation we just defined here. So you see, now you copy. Now when you copy paste this, it returns a string, which is not good. Okay, now Control Shift N to make it typeset. Oh, beautiful. Now let's try to run it. Shift Enter. Fantastic. Okay, so what is this? This is sine and cosine. You want to do the pedal of sine and cosine. And what is this? Information usage text. Okay, that's not good. line spacing. Why do we have line spacing? Yeah, okay. So that's some artifact from this. But anyway, let's try this again. So 0 to 2 pi, yeah, so you need to say plot range, okay? Plot range and plot range, I don't want all. So plot range x and y, x from, let's say 2 to 6, 2 to 7, y from oh, we got a style here. That's fucked up. That's why you got this thing. Hold on a second. Let's try again. Yeah, okay. So you need the plot range y from negative 2 to 3. Let's just say that, okay? Copy. Okay, let's put the plot range there. Let's see. Fantastic. Oh, right. This is sine and cosine. So let's say negative 1 to 1, multiply them by 3. Same thing here. Negative 1 to 1, multiply by 3. Enter. Beautiful. Right. So this negative pedal, the negative pedal of a circle with respect to a point inside the circle gets you a ellipse. Can you see? So if you want, so let's say increase the plot points, 40. Fantastic. So you see, so this shows the relationship, one of the relationship between a circle and ellipse with respect to the ellipse focus. I believe so. Okay, don't take my word for it because you need to check the mathematics, but visually it seems like that's the case. So this is about a property of negative pedal curve. Okay, so but we need to update we need to add the plot range because otherwise it just, otherwise it shows the whole thing. It's not good. So we make the plot range, we update the documentation. So this actually we don't want to use that. So it's it's showing the backslash square bracket pi is because when you copy it shows that because we are using typeset pi there, you see. So if you don't want the typeset pi, you just Control Shift I to turn it into a normal input form. Okay, so now copy paste. You see now you got the normal I and you got the multiplication sign, which can be a space, but if you want to be verbose you can have it. Okay, so that is that. Okay, so make it one line and let's delete our that. Okay, so we got things done one by one. So let's copy the all and we can actually select or paste, run it. Okay, and then we copy the documentation here. Let's see, we can copy that, paste. Good, now it's much better. Yeah, so fantastic, beautiful. So are we done yet? Mostly. Okay, so remember my job, what I want to do is to update, modernize this function definition. And here you see I don't have formatting, so right now I'm using Xah Wolfram mod. It's free online. So here's the source code, Xah Wolfram mod. So about 3,000 lines of code, but most of it is the Wolfram language, 7,000 symbols, you see, 7,000 built-in functions. So if you want the code, you can just grab it on GitHub. It allows you to code Wolfram language in Emacs. Okay, so that's Xah Wolfram mod. But yeah, one feature I don't have is that I don't have formatting code. So I want to format this code, for example. And then you need to like tab, kind of like that. You see, I don't want to do it manually, and I don't want my code to do it manually. I want a function that automatically grab a function, a valid Wolfram language source code, such as a function, to then reformat the whole thing. One button press, reformat, like Go format, like Deno format in Go language and JavaScript. So I don't have that function. So right now, I can do it with Wolfram language. You see, I paste it here. So you got a code. Then you copy it, and paste it back here. Paste it back. You see, Wolfram language formatted for you. See, so you manually go to a trip to Wolfram language. So I still need to figure out how that is done. So I can incorporate the pretty-file formatting in my Xah Wolfram mod. Okay, so now this part is, we can just delete that. Okay, so now we did many things. We cleaned up the code. Is there something else we want to do? How long have I? 40 minutes. So far, so good. Okay, so maybe that's it, or maybe is there something I need to do? Something else. Okay, so there's another question. Okay, so yeah, so another question, which is about the definition of a function's optional parameter. You see this part. Now, to explain that, you see, let's go back to Wolfram language operators. Let's go to Wolfram language definition of a function. Define function. Let's open it. New tab. By the way, Firefox now got vertical tabs. So guys, you need to upgrade, and it's a great feature. So Wolfram language define functions. Now, our issue is about defining optional parameters. Okay, so let me explain. Let's not. So this is a topic by itself, because when you define a function in different programming languages, there are a lot of issues. There is sequential ordered parameter. That's one thing. That's the most typical. You just a list of things. Each argument has specific order. Order matters. Then you got optional parameters. So what happens if some of them are missing? Then you got default values. So optional parameters, that's one thing. Default values is related, but not entirely the same thing. Default value is a separate thing. So ordered arguments, optional parameters, default values, that's another thing. Then you have rest parameters, which is like you might have lots of more parameters. For example, plus addition. You could have 10 arguments, 1 plus 3 plus 7, or just one argument, or infinite, or lots of. So you got so-called rest parameters. Then you got named parameters, which allows you to give a name, because otherwise you just got a bunch of values. You forgot which one is which. Imagine you're gonna launch a missile. There's a function, launch missile. Then you got 10 buttons, launch it fast, launch it within 10 seconds. Then the third argument is launch via submarine or something. So you got true, false, true, false. But you don't know which one, when you call the function. So that's when you need named arguments. Then you have like launch via submachine, then equals to true or false. Then each one is more clear. So anyway, so you got rest parameters, then you got others, I forgot. So in each language they have support for some of these, and they have different ways to do it. Okay, quite many varieties. In some languages they don't even have like parameters in the function declaration, like, because they automatically, whatever argument automatically becomes an array. So then you have a special variable to access that array. So very different from different languages. So there's a design issue. First of all, the issue about mathematically about the parameters of a function. That's one thing, like optional, named, ordered. Then there's the programming language issue about them. Okay. Anyway, so what we want to do, so what we have here is these options parameters. So you see what that does is, you see we use the option. You see plot range. You see plot range is an option in graphics. There's tons of other options. For example, options, and let's call, I want to see all options in graphics. You see, so you got axis, you got color output, you got axis style, you got baseline position, you got grid lines, whether you wanted to draw the grid, you got frames is like the border box around the graphics. You can have the border box, and then you have frame ticks, whether you want ticks on the frame. Sometimes that's useful. Then you have axis, true or false, whether you want the XY axis. And also you see there's no numbers there, so you can also specify axis ticks, that's this one. So you can say at 1, 0.5, 0, 0.5, 1, 1.5, or what other, so you got these options. So but these options are part of graphics but not part of the function I'm defining. So these options, I want to pass it. You see this option, this option, I want to pass it to graphics over here. So that is what I'm doing. So but there is something about that I might want to change. I don't remember at the moment, so let's look up. The situation is the way I'm doing it. You see this style, the way I'm doing it is kind of old-fashioned. It's like 30 years ago. There's a better way to do it. So it's kind of explained here. Okay. But let's not do it. It's getting, that would get a bit technical. So okay, that's it for today. Thank you guys for watching. I think that's it for today. 50 minutes. Okay, so this thing I need to think about offline. Okay, so let's see today's work. So delete that. Okay, so let's see. So delete that. Let's see. got that. Okay, so delete that. So this is today's output. Good. So we clear the function, we define the inline doc string, then we define the function here, then we call it. Okay, so good. So now put it back, syntax correct, showing browser. Fantastic. Bye guys. If you like my stuff, pay me, okay? Go to xahli.info, my homepage, then scroll all the way down to the bottom. Patreon me, Amazon gift card me, PayPal me, okay? Bye. Choker man, bye. Hey, bye. Thank you guys for watching.